Okay. Okay, now we are recording again, so this is official now. Good. I'm sorry, but I'm still learning how to use this thing. So we were saying, we're speaking about taxonomy, and I'm saying that we are going to use the website, and most of the thing we are going to do is based on the website. And the thing that the minimum that I expect you to learn from this course is how to use the website. If you want to do something advanced, I recommend you to learn to use the e-tools. It can be practical if you are going to work a lot with sequences. But I understand that in most cases, right now, you are not going to need it. Most of the things that we need are going to be solved easily with the web. And in particular, you remember the recommendation from NCBI is start with gene. And they do this because many people work with the same gene in different organisms. In my case, I mostly work with one organism or one group of organisms that are closely related, and I don't care about the gene, I'll take all the genome. That is what I do with metagenomics because I get all the genome. So, and for me, the approach is started with the taxonomy database. So taxonomy, interestingly, is a classification. Basically, if you look in the dictionary, this is, by the way, where they took from the dictionary, is the practice and science of classifying things or concepts. Well, concepts are, but physical things or things that we have in our mind, ideas. That includes the logic about how to classify. Taxonomy is also, it's kind of the science, no? And it started with biology. So when people say taxonomy, they tend to think in taxonomical biology, but it can be used, I mean, today taxonomy is used for anything that it has to be with classification. For example, something that I discussed in the methodology of science course is the Bloom taxonomy, which essentially is a way to classify the thing, how we learn and the things that are important in understanding. So I am putting the links, you can follow them later, but just to be clear, taxonomy is not something related to biology. The other taxonomy that people use a lot is the taxonomy of topics in the books. If you go to the library, you probably notice that the books have a number. That is the Dewey Decimal Classification that essentially assigns to every topic a different number. I probably have some book. I don't have a good book at hand here, but good that are classified, well classified. They have, they tell you what is the classification. No, I don't have it here. Maybe this one. So, for example, the book that I typically read are in the 500. But if you are doing literature, you will get 800 or 900. And then you have inside that other classification. Let me see. Do we have something here? No. No, I don't have a good example here. And the point is that you can have taxonomy beyond biology. You can have for books. You can have for ideas. But in biology, taxonomy essentially means that we are grouping together things that have quotation the same category. So initially, obviously, this was done with the thing that people can see. So Linnaeus and to be honest, taxonomy, if you go deeper, you can get something like Aristotle, that was classifying the animals and the plant. Or maybe even before. Aristotle is famous. He made a classification that is well known, but it's not necessarily the first. In other words, we have been classified as humans. We classify the world in groups for a long time, and we do that with the thing that we can see, the phenotypical characteristic. So you say, for example, is it flying or not flying? Is it moving or not moving? So the first classification was kind of, it is alive or not. So animal, vegetal, mineral. Then animal and vegetal are separated because one can move, the other cannot move. So people believe that mushrooms were plants. Eventually, as science advances and we learn more things, you get better things like separated plants for fungi and things like that. So nowadays, taxonomy includes genotypical information. Since we have access to DNA, we have access to information that people didn't have before. The other important thing of taxonomy is that it's hierarchical. So if you put more characteristics, you get more finite. Like you first split in a big block of things, and then you go in more and more detail. So I forgot to prepare some. Anyway, let's see. If we need, so from the theoretical point of view, a classification is essentially a separation. There is something in the door making noise, sorry. So the set of all things is separated in several groups, like you separate animal and vegetal and, sorry. Sorry, some bad unexpected. So you have a big set that you separate in small sets, and that small set are covering all the big set. So all the animals, or all the living things are separated in groups, and everything belongs to some subset. The elements here are organisms, plants or animals or cells, whatever. And the sets they belong are the groups that we are classifying together. The first point is that it should be exhaustive. Everything is classified somewhere. That is the first rule of taxonomy. Everything has to be classified somewhere. The second point is that this classification is exclusive. Like if you are in one part, you are not in the other. So the sets, the subset, this equivalence class are disjoint. This is a key word that I want to give you today. Disjoint means that the two sets touch, but they don't intersect. In other words, you are A or B, but not both. You cannot be in two parts at the same time. Okay? That is a basic rule of a classification set. In the case of a taxonomy, we have the issue that we do it hierarchically. So we have a first separation of the set in big groups, and inside every group we separate again, and inside every group we separate again. So we get to very small classes, but these classes are contained in bigger classes. The point is, one subclass belongs only to one superclass. In other words, mammals are all vertebrates. You don't have mammals that are not vertebrate. Okay, so once you separated the big set in a smaller set, the new classifications are always compatible with the previous one. Okay, you never mix things. You follow me? I mean, I guess you have the intuition, but I wanted to give a formal definition. So you have at the one level some separation, and then a second level of separation that is compatible with the first separation. Okay, every new class is split in small classes. Okay, here I am using the word class in a mathematical sense. There is a taxonomical sense, but we should not be confused. Since you follow this structure, it makes sense to think of the taxonomy like a tree. But this tree is something that we make in our minds, okay? We essentially understand the world in a way that we have everything, and when we separate in small parts, and when we separate in small parts. I have to emphasize that this is something that we choose to do. This is not necessarily a rule of nature. It's not that nature is separated in the tree shape. We understand the world in this way. We put the tree in nature. It's our decision. Now, when we say tree, I'm not speaking about a physical tree. I'm speaking about an abstract tree, which is essentially a structural thing like listing R, in which you have two kinds of things. You have nodes, like circles, and arrows connecting this node. And now this arrow go from father to child. So you have a parent node that can have several child, and every child can have their own child. And the basic rule is that one parent can have several child, but every child has only one parent. This is super important. It essentially means that a group that is in one category, it can be only in one category. You don't have two ancestors. This came from the point that when you do the division, all the division is inside the big division. I will try to make a drawing in a minute. This screen is the universe, no? Introduce this so I can see. Okay. And I separate in two parts, let's say. Let's say that is my initial classification. So I have 4 parts. This is group 1, group 2, 3, and 4. As you see, they are covering everything and they don't touch each other. The border is very, very, very thin, so the intersection is empty. Inside each of these, I have other groups. They can have any shape, of course. But the point is, these new groups are completely inside. What cannot happen is this. What cannot happen is that I have a group that is half in one, half in other. If this was the case, let me put this, I will call this 2.1, 2.2, 2.3, 2.4. Okay? And if this was the case, what is the name? 3.1, but 3.1 cannot be inside 4, no? So this, they dried since the last time I used it. This cannot work. So the basic rule of classification here is that everybody should be in one and only one part. So let's delete this thing. Okay. Now, this condition that every small box is inside a previous one, we can even keep dividing inside as much as we like. As you see, every new division will give you a small set. So you have less objects in every set. But at the same time, every division is kind of more specific, but you require more conditions. So if you put more rules, you have a smaller sets. Okay, so this drawing will naturally correspond to the other representation that you probably know, in which you start with a point that represents everything, and then in this case we separated in class 1, class 2, class 3, class 4, and each one of these is separated in their sub point. This was 2.1, 2.2, and so on. Okay, so just to give some names. Each one of these elements here are called nodes in a tree in general. Let me put the general thing. These lines are called edge. No, it's with G, edge. And this particular, there is the one that without any father, it is called root. So the relationship is like, so let's say this is a parent, and this is a child. Sorry, orthography. Come on. You have to talk. I cannot see you. You move your head like I was
Yes.
looking at
Oh.
you. But,
Okay, yes.
That is why everybody has a microphone. Okay, so there is the relationship, and the basic rule, remember, one parent, many childs. One parent and child.
So childs are leaves right now, right? In the tree.
I know, but this is different. We have not get to that point because this node here is child of the root. You can have several, but you get to the last word here. The relationship of parent and child is given by the arrow. When you every time you have the edge, there will be one parent and one child connected by the edge. The edge essentially connects parent and child. But what you are saying is this: some of these nodes don't have child. If a child is 0, then it's called leaf. Okay. If they have children, okay, they drive since we got quarantine. Let me have another one. If you have children, this is called internal. Okay, internal nodes don't have child. Tamam?
Tamam.
See, I invested in this class. Okay, so that is the general thing. Now, I want to give you a little change of name that we use in taxonomy. This one. All the nodes, okay, let's say, so nodes can be internal or can be leaves. So there are two kinds of nodes in that sense. No? If you have child, you are internal. If you don't have child, you are leaf. In taxonomy, instead of node, we say taxon. Let me write it more clear. This is the keyword. A taxon is some element in the taxonomic tree. Okay?
Okay. Is taxa plural form of taxa?
Yes. Yeah.
Okay.
Yeah. In fact, I was thinking that since I checked it yesterday in the dictionary, and they say taxon, tax. In Spanish, they use different, but in Latin is as you say. Yeah, a single taxon, and the taxa is the set of taxon. Okay. Edges are the connect nodes, and there is a okay. That is the graphical representation of this. Okay. Next one. There is a here. Well, I should have some, but there are kind of levels in the tree, no? And the original hierarchy, the name given when Linus made this thing, are well, you probably know this: domain, kingdom, phylum, class. Domain was kind of animal, mineral, vegetal, but the point is today, and especially in Eukarya, people have some like subdomain, kingdom, subkingdom. There are things in between. But this is the basic idea. There is a ranking of classification, the big like coarse level and fine level. No, like, or let's say this is kind of low resolution and this is kind of high resolution. Okay. All these are taxonomy. All these are taxa. So a particular organism belongs to a species, but belongs to all of these. So you have all of these attributes. When we give the complete list of attributes, we call it lineage. I don't have it, but lineage. You know the word lineage, no? Well, I will show it later. Lineage comes from Linnaeus, the guy who invented this thing. But in practical terms, we normally use, according to the same rules, we call this binomial nomenclature, in which every organism gets two names. When you say Homo sapiens, or Escherichia coli, or Saccharomyces cerevisiae, it's always with two names, isn't so? So, and it's taken from this, essentially you take the last two, the genus and the species. Now, there is a couple of things that I want to comment here. The genus comes from the word general. So when you say the genus of some organism, you are saying what they have, all these organisms, what they have in general. And species say what is special about this organism. And that is a very good way to explain what is something, because especially when you're talking about something new, you are going to show things that, I mean, if it's something new, how you explain something. So you start saying, okay, a kangaroo is like a dog, but it's jumping. I don't know. A koala is like a bear, but works in trees or eat bamboo or something like that. So I always use this example about Australia, you know, because when people try to classify animals in Australia, they have this problem of trying to see, this new thing that I have not seen before is very much like something that I knew before, but with some difference. So the thing that they have in common is the genus, what they have in general. And the thing that they have special is what makes a species. The specialization is what makes a species. Okay. If you like to watch movies, for example, or maybe music, okay, let's talk about this. When I see Netflix, for example, they have like, you can choose the genre of the movie. Are you seeing an action movie or a comedy or a documentary? These are a taxonomy of movies. And then inside, I don't know, documentary, you can have different kind of documentaries. Inside of action movie, you have different kind. So you can also have a taxonomy in other things beyond biology. But instead of genus, we say general. Now I have an issue with that they always annoy me with music. When people try to classify music, according to Turkani, it's like music that makes you sleepy or not, and that is the taxonomy. But when people classify music, I have the problem essentially that there are a lot of intersection, meaning that some song can be in two classifications at the same time, and then you have songs that don't belong to any classification. So it's the taxonomy that people use for music is not very well done. So
I think it's also same for the movies, like science and fiction and action and adventure.
Yeah, fantasy. Yeah, difference between fantasy and science fiction is super hard to pinpoint. And yeah, romantic comedy can be drama also. So it can be romantic, can be drama, and can be comedy at the same time. So, no, but you know, I will tell you what is my point. That if you go to, I don't know, Spotify, you will find jazz, very well separated, and rock, very well separated from classical music. Now, I am not an expert, but I remember something I saw that they say rock, if you go back, you essentially get to classical music. So some people argue that the first metal band was Wagner, who was playing with metal. And the first satanic music were Paganini. They were... you know this hard rock music, like what make music to be satanic? You know what make the music to be satanic?
Metallic sounds?
It's a particular sound called the tritone that sounds very disturbing, and it's a music that in the Middle Age was forbidden. The Catholic Church forbidden this thing because it considered to be sinful. It's something that it has been forbidden for 1,000 years because it's connected to devil. Because it's kind of similar to good music, but it's not good music. So it tries to be God, but it's not. So there's some kind of theological thing. It's not something modern. So it comes from medieval times. So, but the other point that I have with music is then they have a set called late Latin American music or Latin music. And in Latin music, you have salsa and bachata and things that to me are very, very different. And I mean, it's not what I understand by Latin American music. It's kind of the music that people play in Miami. For Americans, kind of Latin America is Miami, and maybe Central America, but it's not the music that we listen in South America. So they put in this big bag all these people speaking in Spanish. That is Latin American music, even if the music is super different. So where you put? There is another story that you probably don't know. In the 80s, you may know there was a war between Argentina and England. You know, the Falkland Island. Well, there is some island that belonged to England in front of Argentina. And in the 80s, Argentina invaded them and they had a war for 2 months. So at that moment in Argentina, English music was forbidden. So people cannot listen music in English. And that makes that people start making rock in Spanish. And for a lot of time, a lot of people make very good music and they get promoted because if you don't have a market, you never get published. So the only good thing about that war is that we have a lot of Spanish, rock in Spanish, let's say rock in Spanish, that developed during the 80s and 90s. Is that rock or is Latin music? Okay, so okay, I'm talking about things that are not biology, but point is that taxonomy are complicated.
Did Argentina win the island?
No, okay, they think. No, the bad thing, people die after thousands of dead people. They stay in the same position. It was very. I was very young, so I was not the kind of the people who can go to war, but I knew people. I mean, it was very important for my generation because the kind of young people who are going to the war and dying for nothing. So, very sad. Anyway, okay, going back to the point. Taxonomy is not phylogeny. This is an important topic. Let me you read what I say, no? Because we tend to think that if it's a tree, like phylogenetic tree, then they are taxonomic tree. And to be honest, it's a mistake that I have made before. But since I made the error, I learned from that error. I don't want to do it anymore. So it's important to realize that even if taxonomy is based on phylogeny, phylogenetic trees are not taxonomic trees. And let me show you. In a phylogenetic tree, you have one sequence and you have another sequence, and you find what they have in common, and then you will have another sequence here, and you will eventually find that they have something in common. But for one side, all these are species, and this also. So the common ancestor of two bacteria is also bacteria, okay, in general. But these are also species. In the phylogeny, philos is kind of a family, and genus is how it generated, how it created, how the family become what it is. Okay, So phylogeny is something based on the idea of molecular evolution, the idea that the DNA of two bacteria or two organisms came from the same ancestor. There is a, I mean, if two sequences are very similar and they have a small number of mutations, you can essentially guess what was happening before. This one that we have here are the sequence that we can see today. And these species that we reconstruct upward in a phylogenetic tree are inferred, are like predicted. So we can predict what will be the sequence of the common ancestor of the some bacteria that existed millions of years ago and what they have in common. Okay. The second point is that, well, this is very clear in bacteria, but if we are speaking about plants or any other sexual organism, you have something that should be very obvious, is that every element has two parents. Okay? What is the name? In eukarya, when you have a sexual reproduction, every element has two ancestors. So it may happen that a given species has ancestors in two different taxa. It may happen. You know, for example, there is some evidence that suggests that modern humans have part of Neanderthal DNA, and Neanderthal are a different species. Or if you have a mule, for example, you know, there's some kind of mixed race. Like you can have the crossing of a lion, of a tiger. They can have babies, and horses and donkey can have mules. These animals exist, and they have ancestors in different taxonomic branches. So what is the taxonomy of a mule? I don't know. But certainly the phylogeny of a mule is not the taxonomy of a mule. And I should have put down the stuff here. Anyway, you were saying something, Ahmed?
I was saying they're not species, are they? Because they can't reproduce. They're just...
Well, technically, and that is a point that I wanted to carry, is this. In the case of eukarya, the limit that separates two groups is what you say. Let's say different dogs belong to the same species because they can have children, and the children are viable. They are fertile. Okay, the children can have. If they have children and the children is not fertile, then we say they are in different species. But clearly, humans and Neanderthal had children, and the children are fertile because we are here. So if they don't reproduce, they are different species. If they reproduce, but the children are not fertile, they are different species. But in some cases, even if they reproduce and the children are fertile, they are still in different species. That can happen. Okay. So the condition is in one sense. If they are, I mean, if they cannot reproduce, they are certainly different. If they can reproduce, but the children is not fertile, again, different species. If they can reproduce and the children is fertile, it doesn't mean that they are the same species. You can still have different species having fertile children. That is the case with humans and Neanderthal. They are different species, but they have children, and the children are fertile.
But the fertilization is not the key point for the bacteria, because you draw bacteria
Exactly.
in the board. How can we say that they are in the same species or anything?
Exactly, that is the point. The point is that in eukarya, we have a rule that is very well defined to separate. So if you cannot have sexual reproduction, they are different species. But in asexual organism like bacteria, how you define a species? That to me is an open question. That to me is an open question. So there are some rules, and they are basically connected to some gene markers. I will talk about this later with more detail, but the basic point that you say very correctly is that the limits are not very well defined. But just to take an idea, you take the 16S gene that all bacteria have and is super conserved. So if two bacteria have the same 16S gene, we say, okay, they are the same species. If they have the same exactly, 100% the same. If they have some difference, let's say 10% difference, they are very different. 10% of change on the 16S is too much. So they are different species. But there is something in between. What if you have 97% similar? Are you the same or not? That is kind of the limit. People normally say 97, but it can be 95, it can be 98. It's not very clear. So in other words, sometimes it's very obvious that two things are very separate. In that case, there's no problem. But when they are very close, and you don't have a rule like sexual reproduction, it is not very clear how to put limit. And that leads to a lot of problem because, as I say at the beginning, this taxonomy is something that we invented. It's not something that exists in nature. Taxonomy is something in our mind. It's not something in nature. Let me share my screen again. Do I have? And in particular, that means that with time, taxonomy change. There is no there is no official taxonomy for two reasons. One is because there is nobody that can say this is official taxonomy. There are some efforts of different people trying to make a taxonomy. There is a kind of general idea of more or less what is the taxonomy, but it changed. NCBI has a taxonomy that is what most people use. I mean, at least in the work that I do, most people use NCBI taxonomy, but it not necessarily official like the species names. I mean, even the species name can change. So we have the problem of this is temporal and this is not super official. It can change with time. The bacteria are the typical case. We say this thing, no? Each element in this database is every taxon has a number. Like everything in NCBI, everything in the database, everything has an ID. So let me show you 1 second and I will tell you a comment about one organism that I have the experience of having trouble. So in NCBI, again, taxonomy, let's go to taxonomy. There's something like taxonomy browser. And here you have the first separation. So let me go to bacteria. And here you see the basic tree. Is this a tree because they are separated in a given way. So let me show you the organism I was looking for. This was Acidithiobacillus. This is the bacteria I used to work. So this is a genus, and there are several versions. So the one that I worked is this one, Acidithiobacillus ferroxida. So let me just, in the last 5 minutes, tell you what is this. Acidithiobacillus ferroxida, the name says, is a bacillus that live in an acid environment. Thio means sulfur. It can take sulfur and it can take iron. Okay, it can oxidize iron. Ferroxide means it oxidizes iron, and in acid sulfur. So we had this one working with iron and sulfur, And there is two comments. There is something else called ferrivorans. And if you look, these are different species, but the story is this. When they discovered this branch, the first ferroxidans was isolated, is today these ferrivorans. So what I mean is this. They found a bacteria, they put a name, they found more bacteria with the same name. And after 10 or 20 years, they found that the first bacteria that gave the name to the family was not in the family. So if you look at the history of this organism, it changed from one part to the other. Then there is another, this one, I studied the genome of this bacteria, and what happened is this. Before sequencing, this bacteria was not called Thiobacillus because it didn't have the capacity to grow in sulfur. So the acid Thiobacillus can grow in sulfur or can grow in iron. This particular cannot grow in sulfur because it is missing one gene. But after we sequenced the genome, we found that you had all the genes for sulfur except one. There was one gene that was broken, that essentially means that before we got the sequence, this was classified in another genus. And after we got the genome, we found that all the genes are very similar to the rest of the family or the rest of the genus, except one gene. In other words, when we classify the organism given the phenotypical characteristics, we get one result, but when we get the genomic characteristic, we get a different result. So that is the point here. The taxonomy may change. Now, we are finishing now because you have probably another class, but what I want to show you here is this. As always, you have an ID. So in my case, what I normally do, I try to remember this taxonomical ID. Since I am working with bacteria in a given genus, I try to go to the taxonomic ID of the genus. So here you have the lineage, as we say, all the ancestor. You have starting with cellular organism, bacteria. This is the, you see, superkingdom, phylum, class, order, family, genus, and species. And this one in particular is inside the species. This is a strain, a kind of subspecies. Now, normally I will work here at the level of the genus. Or if you get a species, you get all the strains of the species. So please look that here we have two sets of data. Next class I'm going to discuss this with a little more detail, but the point is that some are associated with the species and some are associated with the strains. There are other names that we have historically, Ferrobacillus sulfoxidans, as you see. So names can change with time, classification will change with time. So to me, the safest way is to keep this number. Sorry?
How about, I was gonna ask the number. Is the number changing over time or is it staying still?
Well, yes and no. The number doesn't change in the sense that the taxa doesn't change. You create a taxa and you put it you get a number that doesn't change. I mean, at least this is the taxa I've been using for 20 years. But a particular organism can move from one taxa to another. I mean, when an organism is reclassified, it can move from one taxa to another. Okay?
Okay.
So the tree doesn't change, but who is in every position of the tree can change. Okay?
Okay.
Okay. Okay, next time we take a look at this again. But just to give you an idea, I normally say tax ID and I put the number. And I think, I don't know if I need to put a space or not. This is the way I start to make sure that I'm looking at the organism that I want. Well, I'm not sure if I put text ID. Okay, here, without the space. I got all the things, and one genome. So you see, when I put TXID and a number, it's another way to declare an organism. So in other words, if you look for genus or species, you can have the common name, the scientific name, but also an ID. Okay, and IDs tend to be more stable. The name can change, but the node will be the same. Okay.
Okay.
Any last minute question? Look, ferroxidin, formerly tubacilloferroxidin. The name changed with time. I will write a little exercise. I will not call it homework. Maybe I will call it homework so you do it. But the basic idea is like, I will take the example that were in the NCBI document and that it translates from English to the query language, okay? How to ask the question. Because it's a basic competence, a basic ability that everybody should have, no?
Yeah.
Find the thing that you want. You should be able to find the thing that you want, no?